Good morning. Welcome to today's mini lecture. We've been discussing and reviewing how to balance equations and the different types of equations. So in our general chemistry, our packet said that there were 5 different types of equations. The the synthesis, decomposition, single replacement, double replacement, and combustion. Well, in today's lecture, we're going to look at these very specifically, and we're going to combine them a little bit for AP. And instead of saying that there's those traditional 5, what I want to do is I want to group them a little bit different. So now we're going to say that a synthesis and a decomposition, because they are mirror images of each other, they're the same equation. So that is one type of equations. Now, we also had double replacements. If you remember, in a double replacement, you have a compound plus a compound yields a compound and a compound. Well, if you have a very specific, starts with an H, acid, ends with an OH, base, an acid-base reaction, then we classify it as a neutralization reaction or an acid-base reaction. So it's a very specific type of double replacement. Now, we never really talked about the driving forces in a double replacement. So I'm going to skip down to here. It's called a precipitant. We said that driving forces were when 2 ionic solutions added together and the product was a solid, and that solid would precipitate to the bottom of the solution. Well, if we look at this right here, it says that I have potassium carbonate, and I'm adding it to magnesium nitrate, and then I'm going to get a potassium nitrate and a magnesium carbonate. But if you look, these little signs, little abbreviations afterwards, AQ means aqueous, L means that it's in its liquid form, and then S right here is a solid. So that is a precipitant. So that is my driving force. We're going to address this a little bit more as we go into equilibrium and kinetics, but the driving force is what determines the mathematics that we use to determine where equilibrium is established and things like that. So if you look at this, this is called the net reaction. So then, if you look up here, we have oxidation reduction reactions. This is the one that I want to address in today's class. This video is specifically looking at oxidation reduction reactions. And basically what an oxidation reduction reaction is when you have a change in the oxidation state of an element from one side of the yield sign to the other. So if this is a solid, all solids must have an oxidation number of 0. So I started with a positive 2 and I went to a 0. Now look at something that you've never seen before. In a balanced equation, have we ever addressed the actual electrons? No, we just always assume that the electron charge on this side is equal to the electron charge on this side, so they're just automatically canceled out. But when we're doing oxidation reduction reactions, we do look at those electrons. So that brings us into today's notes. And today's notes is going to be focused on what is an oxidation reduction reaction and how can you determine what is being oxidized and what is being reduced. So first of all, in an oxidation reaction, then the atom on one side of the element, over here 0, oxidation state, is going to change and it is going to lose electrons. In a reduction reaction, it is going to gain electrons. So you say, well, how can you remember this? Well, your book uses the word oil rig, and that's oxidation is losing, reduction is gaining. I have always used Leo the line says Gur. This is the one Mr. Vance was taught whenever he was taking chemistry. Leo, meaning losing electrons, is oxidation. the line says gaining electrons is reduction. Does it matter which one? No, but it's just a lot easier if you have one of these. So first thing I would like to do is I'm going to let you read through these notes by yourself. Just make sure that you can assign oxidation numbers. Excuse me, guys. There we go. Make sure that you can assign oxidation numbers. So we said that an individual element or compound must have a total oxidation state of 0. So the way that I do it is I work above it, because we already know that calcium has to be a +2. I have 1 calcium at +2, so that gives me a total contribution of +2. Fluorine is a -1, and I have 2 fluorines, so that's going to be a -2, because 2 times -1 is -2. Then when I add these two numbers across the top, I get +2 plus a -2 equals 0. So what is going to be the assigned charges? And it would be the calcium is a +2, and then fluorine is a -1. So we talked about this one a little bit yesterday, the peroxide, but I want to still do it same way. So I'm going to put a 0 here. We know that this is a +1, so therefore when I do this, that makes this a +2. But this time, guys, if I just said that oxygen had a -2, that would be -4, and it wouldn't be a stable compound. So I have to start asking myself, what can I add to +2 to get 0? And of course that would be -2. So if I have 2 oxygens, oxidation state is -1, that gives me an overall -2, which is 0. So in this one, the hydrogen is +1 and the oxygen is -1. If the oxygen is -1, it is considered to be an oxide. All right, so I'm going to skip this one. I'm not going to do any organics right now. I want to come over to this one over here. This is what we're going to be doing a lot of. And again, let's put it at 0. I know that the potassium is +1. I know that the oxygen is -2. I always get somebody who says, how did you know oxygen was -2? Well, let's just go through and look at it first. We got a +1 on the top. The oxygen is not by itself like over here, so it has to take its original -2 charge like we always would assume. So that's going to be -8. So what can I add to 1 and -8 to get 0? The answer is +7. So in this one, my Mn has a charge of +7. And I would like to do the last one over here. So on this one, do you see how I'm not dealing with a SO4? It's an SO4 -2 ion. So I'm going to set this even, not to 0, but -2, because it has an overall charge of -2. So this is going to be -2. I'm sorry, I wrote it in the wrong spot. The oxygen is going to be a -2, and that gives me a total of 8. So what would I have to add to -8 to get -2? The answer would be +6. So that +6 has to be the overall charge of the sulfur. And I always get somebody who says, well, Mr. Vance, that doesn't make any sense. I thought sulfur was -2. Well, always remember, this is going to be a covalent bond. It's a molecular compound. So even though it is not an ion, then it is going to take that dipole-dipole charge, and that is going to give it a +6 for the charge. So sulfur would be +6. All right, so what I want to do now is just go through and assign and make sure that you can do oxidation states and who's doing reduction, who's doing oxidation. So I'm going to go ahead and stop the video here, and then we'll do another video for assigning Leo the line says GER.